Well, we only got 3 folks today.
I guess they run off. They're scared.
Oh, it's hard. Hard to come up. Welcome, everyone. Give me a moment. I've got a few things I've got to get set up really quickly, and then we'll get to lecturing. Of course, I sound a lot more clear on the video when I don't have a mask on.
I can hear you fine.
Okay, that's great. There you go. No problem. Do you want a lunar sheet?
Yes, please.
Awesome. Go.
Is this for the assignment that takes the 24 days?
Yes, sir.
Okay.
And like I said, you can always print one off if you want, but there's one. Okay. So just a little bit of administrative stuff really quickly. My camera's been moved. Awesome. Let's go into Blackboard real quick, just to make sure that everyone knows, again, how to access stuff. First, remember your lunar observation is down here. You can start it whenever you want, submit it whenever you're done. The due date is on it. Your journals are in here. I haven't graded journal 1 yet, but I'll be grading that tomorrow. Journal number 2 popped up. Please do that one. Textbook and assignments, all that seems to be working. I checked this link earlier. Please get in there. All of your homework assignments and your test will be due on the 6th. I'm going to go ahead and move those there now. Now, they're not going to be visible to you yet. I'm going to have to go in later and make them visible. Nothing's ever easy. But please be aware it will be homework assignments 1, 2, 3, and test 1 that are all going to be due on the 6th. So I recommend you getting started on them, like at least taking a look at it tonight or tomorrow. Because as soon as I get back to my home office, I'm going to make these visible for you. I'll go ahead and make this one visible right now, just to say I'm doing it. Because this one takes about an hour, 2 takes about an hour. They take longer than they look like they do, and some of these questions have multiple parts. So one of the quickest ways to get yourself messed up is by saying, I'm just going to wait till 5 minutes before it's due. And then 5 minutes before it's due, your computer explodes. So go ahead and get looking at these. If you have a question about what was talked about in a lecture, please remember you have access to the textbook here. You have access to the slides that I used during the lecture here. Class 1, 2, 3, 4. They're in order. You might notice there's no 5. That's because one of these lectures takes multiple days. And of course, the videos here. So as we keep going throughout the semester, I'm going to spend less time each day going through all the administrative things and telling you where everything is. I just, at the beginning of the semester, want to make absolutely sure that we have all resources necessary. Feel free to email me as many times as you need to get what you need. Okay, so we are going to follow up from week 2, day 1. If you haven't checked this video out, check it out later, because I'm going to pick up from it as if you had seen it. Um, hmm. We're halfway through this. One moment. I'm going to need this later. So we talked about discovering the universe for yourself. We discovered the reason for the seasons. Please check back on that. Remember, it's the axial tilt that causes the seasons. We discussed the idea of the celestial sphere. And just as a real brief recap, the celestial sphere is an imaginary sphere that surrounds the Earth. And all celestial bodies lie on this imaginary sphere. You'll notice if you look at the moon, it looks far away. If you look at a star, it looks far away. But that far distance is the same amount of far. The sun looks far away. And so we're going to call this imaginary distance the celestial sphere. This is not a slide representative of the celestial sphere. It's just a slide. There you go. That's a celestial sphere slide. We also talked about how you can project everything from the ground onto the celestial sphere. I could talk about the celestial North Pole, the celestial equator, the zenith, which is the point directly above my head. So that's all the basis. So now we want to start somewhere else. All right. Again, my favorite question. Have you all seen the moon before? We've all seen the moon. How big does the moon appear? This big? This big? Somewhere around this size? My question is the moon really this big? No answer? What do you all think on the video recording? Do you think the moon is really this big? I'm going to say no, right? It appears to be that big, but I don't think it really is. Let's see if I have any reason to think that. We're going to use this tennis ball as not really an experiment, but we're just going to see really quickly. Here we go. There's a tennis ball. Can everyone see the tennis ball? Y'all see what size it is?
Yes.
I want you to use your fingers to measure the size of the tennis ball from where you are. All right. Awesome. Now I'm going to change the location of the tennis ball. Everybody keep your fingers. All right. Now do the same thing. That's weird. Did the tennis ball change sizes?
Yes.
It seemed like it changed sizes, really. But that's weird, because it seems to be the same tennis ball that we had before. And usually tennis balls don't just change sizes. So that tells us something that we already knew, but it gives us a more concrete example that things appear to change sizes Okay, now this is not some ground-breaking thing. I have not shocked the world by saying that things appear to change sizes based on their distance away. So when I look at the moon, and I see that it appears to be this big, I can say that it appears to be this big based on its distance away. Now, that doesn't really tell me how big it actually is. It just tells me how big it appears to be. So we want to find some way to measure how big it appears to be. We want to find some way to measure how big it appears to be. Of course, my meter stick is gone. That's all right, I don't need it. All right, first I'm going to draw my observer, Dr. Sarah. That's my observer. And let me draw the ground underneath her. Green. And Dr. Sarah is an observational astronomer, and she is just checking out the sky. So I'm going to draw the sky. That's a dome, right? Now this dome is representing the quote-unquote celestial sphere. Oops. This blue dome is representing the celestial sphere. Remember, it's not a real thing, right? It's an imaginary sphere that surrounds the Earth on which all celestial bodies lie. Everybody understands that? Just making sure. So we're going to measure the celestial sphere. In fact, if I could see the whole celestial sphere, well, it's a sphere, so we would say it's 360 degrees. However, each person can, at one given time, only see, assuming that they're not super high above the surface, approximately 180 degrees. So we'll call this 0 degrees here and measure around to 180 degrees over here. Y'all still with me?
Yes.
Now this makes sense, right? 0, 180. So we're going to say that the celestial sphere covers up, not a radius, but an arc length of 180 degrees because you can only see half of the circle. Sure. Or half of the dome. I'm going to draw the sun now. And all of this is going to make sense at some point. Okay, well, let me try again. There you go. That's my sun. Now, what you'll notice from the sun is it covers up a portion of the celestial sphere. The sun that I've drawn covers up or takes up a portion of the celestial sphere. So in order for me to measure the size of the sun or any other celestial object, I'm going to use something called angular size. I know that was a long way for me to get there, but I just want to make sure you get there. The angular size is the size of an object measured in degrees, or measured by angles, if you will. If I try to measure the sun in centimeters from here, it's going to be based on how close the meter stick is to my face. But regardless to where my compass is, the sun will still take up the same portion of the celestial sphere, which we're going to call the angular size. So don't just think of angular size as the size of an object measured in degrees. Think of it also as the amount or portion of the celestial sphere that a celestial body covers. Let me write that in a different color. Okay, so for instance, the angular size, or also sometimes called angular diameter, of the sun is approximately I'm going to get this out, 0.503 degrees. 0.503 degrees. Is that how big the sun really is? Doesn't matter, right? We know that the portion of our celestial sphere that the sun takes up is 0.50 degrees. Sure, that's going to have a relationship to how large the sun actually is, just like how large this tennis ball appears has a relationship with how large it actually is, but it also is based on the sun's distance from us. Any questions so far? Pretty straightforward. This slide shows where the angular size or angular diameter comes from. I have an Earth and a moon, not to scale, right? In this drawing, we've got the person, and then we've got the moon, and then we've got the lunar diameter here, and then we've got the angular diameter shown here. So it just shows how the angular diameter or angular size is created based on the distance of the object. So here's the problem. The sun is the largest single structure or largest single celestial body that appears in the sky, right? And it's half of a degree, approximately. So using degrees to measure bodies in the celestial sphere, we might need some smaller units. Now, of course, if we're measuring the diameter of a constellation, sure, it might be larger. But singular stars, now we're going to need smaller. So, we've got degrees, and of course it takes 360 degrees for a circle. But we also have something called an arc minute. And an arc minute is 1/60th of a degree. You can think of a degree as an arc hour. And so 1 arc minute shown there is 1/60th of a degree. It also says here 1 degree equals 60 minutes, if you will. So, I might be talking to a fellow observational astronomer. They're like, hey, have you seen that structure in Orion? I want to see what structure. And they'll be like, really, dude? That 3 arc minute structure, which tells me how big it is. But even arc minutes aren't going to quite be small enough. We're talking about stars, which are basically little points of light. So I can go down to what are called arc seconds. And of course, an arc second is 1/60th of an arc minute. So we've got arc seconds. And if we multiply that by 60, we'll get arc minutes. Multiply that by 60, we get degrees. Any questions so far? Pretty straightforward. So I keep checking my phone. My kids are supposed to be on like a therapy session right now, and I'm just like, if they don't get on it, I'm gonna kill them. But of course, I can't kill them now. Not that I actually would. That was a joke. Apparently. So one of the hilarious things is there's an auditor that audits like the online portion of classes, and I just imagine them watching all my videos and being like, "Is this okay? Is this guy fine?" All right, let me keep teaching.
So, right there, is that in arc? Is that in degrees or minutes?
These
Yes.
degrees.
Okay.
The little circle means a degree.
Okay, it's hard to see from here, but I need my glasses.
I understand. Yeah, it's helping me. So yes, apparently this is about a degree. This is about 5 degrees, depending on the size of your hand, obviously. But we want to be able to do more with this. So let's talk about some more we can do. We've already talked about the sun's angular size of about 0.503. For some reason, that amount doesn't seem right to me. I'll check later. We should be able to write that in other units. In fact, let's convert this to arc minutes. I want to convert this to arc minutes and arc seconds if we need any. So this is what we'll do. We have it in degrees, 0.503 degrees. If we multiply this by 60, it will put that value into arc minutes. All I need to do is take how many I have in degrees, multiply it by 60. I get how many I have in minutes. Now it's not going to come out perfectly even yet, but we might have to do some more to it. 0.503, not pi, 0.503 times 60. I end up with 30.18 arc minutes. So that 30.18 arc minutes is the same as 0.503 repeating degrees. But I'm not done yet. What if I don't want any decimals in my minutes? What if I want it to be written in minutes and seconds? Check me out, everybody. Keep the 30 arc minutes. Now just take the 0.18 arc minutes, multiply it by 60, because that will convert this part to arc seconds. So I'm just multiplying that 0.18 times 60.
And 20.
Yes, sir. And I get 10.8 arc seconds. So I can write the sun's angular size as 30 minutes or 30 arc minutes and 10.8 arc seconds. If you want, I believe on homework assignment number 2, one of the questions says, please convert this into minutes and seconds. And so you have to do something like that. And while you're writing those notes, I'll write like a little rule. There you go. I was just writing the steps on the board in case anybody needed it. So basically it says, if you want to rewrite something in degrees into a combination of minutes, degrees, and seconds instead of like decimal degrees, then keep the whole number. If there's a whole number, leave it. Multiply the decimals by 60, which gives you this in arc minutes. Then repeat it again to get to arc seconds, which means keep the whole number, multiply that. Once you get to the point in your homework and see other examples, I think it will make more sense to you. And if I'm going too fast, everybody let me know. Also, if I'm going too slowly, let me know. I know some folks. Yeah, it says repeat to get to arc seconds. So once you get here, you will repeat that same step of keeping the whole number.
So 60 times 18.
Yes, ma'am.
Okay.
Basically, what you're doing is you're keeping the whole part and then turning the decimal into whatever the next smallest unit would be. I'm keeping that 30 minutes, but I'm turning that 0.18 into
So this
arc
is
seconds.
converting.
So what I'm doing here This was what I had original. But sometimes people don't like their values in decimals. Instead of just saying 0.53 degrees, they're like, hey, I want this in degrees, minutes, seconds, for some reason. And so I'm converting from degrees to arc minutes. And then from arc minutes to arc seconds, just so I have as few decimals as possible. The example I usually use doesn't even have that 0.8. So this isn't something that you usually have to do. It's just, you can do it. Questions right now? We got some more stuff we're going to do with this. It'll be super cool. Okay, so here's something that's called the Great Coincidence. And I should take this slide out because it's really misleading. So our moon is about 400 times smaller than the diameter of the sun. And it's also approximately 400 times closer sometimes. So what that means is that sometimes the moon is large enough in the sky to completely cover the sun. Most of the time it's not, right? Sometimes it is. And when that happens, we get a total solar eclipse. Again, this happens on other planets. Jupiter has 4 large moons. The closest one, Io, often causes total solar eclipses on Jupiter.
Which I remember seeing that just a couple of years ago. It was pretty cool.
Yes, sir. The eclipse here.
Yeah, I've got to see 2 in a lifetime so far.
Awesome. There's another one in like 2 years. You just have to go a little north. No, I want to say New York or southern New York. It's not too far north. That was my first total solar eclipse and my first time being able to locate Mercury. So I was super excited about it. Of course, if the moon is the exact same size as the sun in the sky, then like it's the best looking ones, but usually it's like 0.001 arc minute smaller or something, and so it's still total, but not quite as hot. A lot of times we get what are called annular eclipses when the moon does not cover the sun completely. Those look pretty cool, but not as cool. Any questions so far? If you haven't had a chance to experience a total solar eclipse in your life, please check it out. It's weird, I guess, for lack of a better term. Okay. Mr. Palmer, you've talked about celestial spheres and angular diameters and solar eclipses. So what are we going to do with all that? Who cares? Thanks for asking, hypothetical student. Let's find some things we can do with it. All right, first let me clear this board a bit. And I'm going to write down the angular size that the last slide gave for the sun of 0.523 degrees. Can anyone tell me the average distance between the sun and the earth? And feel free to check your notes. That is correct. Thank you very much. 150 million kilometers. So if I know the angular size of the sun, or angular diameter, and I know the distance of the Earth to the sun, I should be able to calculate the physical diameter of the sun. If I know the angular size, how big it appears, and this distance, how far away it is, I should be able to find the physical size of the sun. Let's talk about how we can do that. Here we've got the angular size. Nope, I don't like that color. Here we've got the angular size. There you go. And over here we've got the physical size. And we're going to figure out how to relate these two things. Here we go. I'm going to set them equal, but not yet. I'm going to have to do some stuff before they're equal. Notice on the left side, it says angular size in degrees divided by 360 degrees. So if your angular size is in any other unit of angular measurement, you're going to need to convert this 360 to whatever that unit is. If it's in degrees, easy. On the right side, physical size. That's a 2. That's a pi. And that's the physical distance away from the object. Usually written as x, but I just wrote out distance. And I'm going to go ahead and replace with x in a second. I just want to write distance up there for you all need. So 2 times pi times the physical distance away from the object. Pretty cool, right? But you might be thinking, okay, that's great, but I need this in a form that I can work with. So let me reorganize it a bit for you, if you will allow. I'm going to multiply both sides by 2 pi distance, and now it should be directly equal to the physical size. And remember, this x is a physical distance, so x. Now this seems awfully convenient, right, that these numbers would work out. And in fact, I don't want to just trust them. Let's test them out. Angular size, 0.5333 repeating degrees. All right, let's put that in there. That's already there. 2 pi distance. This distance is at 150 million kilometers. I have 1.5 times 10 to the 8th. Does that make sense? Everybody take a second, see where I got that, why I wrote it like that. So I write this out longhand, that's not where that goes. One, two, three, 6. That's not it. There you go. 150 million, but notice 1, 2, 3, 4, 5, 6, 7, 8. So you can definitely write it like that if you want. Also, I know that's confusing. The reason why I keep writing stuff different ways is so you can see, hey, you can do this, you can do that, and learn how to see them as the same thing. You all right with that? Okay. Make sure, if you're not, let me know. I don't want to mess anybody up because I'm being ridiculous. That's it. I want everybody to grab their calculator out and type this in. If you're using the TI calculators, you can just click in the numbers and it will work fine. 0.5333333 divided by 360 times 2 pi, excuse me, 1.5 times 10 to the 8th. Got a number. Once you get a number, just look up for me. You don't have to tell me what it is. I just want to make sure everybody gets one. And then we're going to go see if it's correct. Number? It's going to be high, right? Because this is high. What we should have done is we should have taken the average angular size, and this is like the large angular size. Of course, the units kilometer are going to be the same as the distance units that you use there. What do you all think? Does that sound believable? You think that the sun has a diameter of 1,396,800 kilometers approximately? That's so big, right? That's huge. Let me write the whole number out for you. So big, right? Or was everybody able to get that about 1.4 million kilometers? No's, yeses? All right, we gotta go check to see if it's correct. And I'm going to Google diameter of the sun. It's already up there. Oh my God, why would you put it in miles? Yes, that's correct, but woo, that feels better. 1.3927 million kilometers. Is that pretty close to what we got? That's very close to what we got. Again, our difference is us using the large angular size instead of the average angular size. BT dubs, the sun is huge, in case you all didn't know that for sure. Goodness gracious. But, so now we see that we are able to mathematically calculate the physical distance of something if I know, or not the physical distance, the physical diameter of something if I know how far away it is and I know the size it appears in the sky. Yes, ma'am.
Why is my number, I mean, it's pretty close to yours, but it's still a little off.
What's your number?
It was 13,95390.
13,539 times 10 to the anything? Let me come check. I'm going to turn on the light on so I can see the calculator there.
I just keep getting an error on mine. I must be.
Okay, well, hey, let's take some time. Let's talk about it.
Well, what it is.
All right, that part looks good. Your number is 1,375,069. Mine's different because I put 0.5 repeating, so my 3 comes out.
But if we had like a test or something, either one would be right.
Yeah, that's great. And you could just do 1.4 times 10 to the whatever power. 6 power.
So clear that off and show me the way you would type that in.
Which the answer?
No, the way you would type it in the equation, like the way you would work.
The exact same thing. Okay? Except on my calculator, I just kept pressing forever, which makes my number long. 0, something we had. Times 2, something we had with 5. And then when I type in that, I usually just say 1.5 into the is fine.
How'd you do that?
1.5 seconds.
Okay, that's what I.
And so that E is times 10 to the power of whatever's next. It comes up to
Alright, that part right there.
Yeah.
Alright.
So good job, you were fine. I'm gonna slide over here.
Oh, I know what you mean.
What do you do? Oh, I'm sliding too far. Oh, you have one of the Casio, so I don't know exactly how to. Did you put 1.5?
Yeah, that's what I'm missing. Is it 2 pi and then 1.5 and then to the E8, right?
Yes, sir.
Okay, that's.
Watch the internet and see if it's in there. Oh, there's just a button for it.
Oh yeah.
Or is there a button for it?
Yeah, well, like right here, you're like 0.533, and then drop that down to 36. Push this over, go to X, 2, and shift for pi.
Can you, do you have to type in times pi, or does it just automatically multiply?
It may not be multiplying it, then maybe Y, so maybe times
Sure, sounds good.
pi, and
Maybe after the times after it too.
probably, maybe we'll see. If that may be the reason. And then, or we can do times 10.
Now, let's make it as easy for yourself as possible. I just want to see if it works. For the folks on the video, I'm just helping folks with calculator stuff, so you can just, I don't know, fast forward it or party. 1.510, and like the 8 is part of the 10 there, so that is not typed in correctly.
Okay.
Remember when I was like, hey, Casio calculators,
Well, this one's been great.
Calculator.
Well, see, I let her.
I've got his.
I mean, I know they work.
See, I don't know how to use that thing. I've been
Your
using
mine's
this
working
thing
now.
all
You can have
season.
that.
Like, he had to show me when we left class yesterday.
It worked on mine, the Casio.
I just don't know how to enter it correctly, so I'm not saying that it does not work.
I got the pi and the and it worked. We come out just right.
Let me see where you entered it.
There you go. It's on that. There.
Okay.
Okay, great. So while everyone, and you were fine, right? Okay. While everyone's finishing up, checking out how their calculator works, I got to pull up a website that I'm going to be able to make work somehow. And I have to use Microsoft Edge for
All
this.
zeros on yours. On that one, okay.
Well, no, the E button still worked.
I hear the laugh when I say Microsoft Edge.
Thank you, sir.
Oh, no problem. Anything that I can do to help. The reason why I have to use Microsoft Edge is because if I use Google, it will block it. Because it's a garbage website. Now it's a great website. Oh, it's working. All right, we got it here. So what I'm doing now is I'm pulling up the lunar simulation. And you can find this on, oh yeah, I forgot, Flash has been retired. I have no idea how to make this work now. It does not. Oh, it use Flash. Anyway, let's just close this off and vamp. So I wanted to start talking a little bit about the phases of the moon. And usually I use a simulator, and I'm going to find a new one. But the one that I did have was a Flash simulator, so I apologize for that. So let's just look at what we have here and start talking about it. Now, I'm sure we've all noticed over the course of our lives that at some point, the shape of the moon changes. As a youngling, I thought the shape of the moon changed. And not only that, I was like, how do people stay on the moon? Wouldn't they just fall off the little hook part down at the bottom? But what was really happening is the moon is not changing shapes. What's really changing is where the moon is in relation to the Earth. So let's draw it. If only I could change any of this. All right. So I am starting off here with no moon. We have no moon, right? There's none. We got Dr. Sarah right here. She's hanging out. There's no moon. I'm now going to draw the moon at some point in its orbit around the Earth. I'm going to draw the moon. There you go. Notice how the sunlight is here. Remember, the moon does not produce its own light. All of the light we see from the moon is the light that's reflected from the sun. All right. But notice only half of the moon is facing the sun. And it's going to be the half of the moon that's facing the sun that is illuminated. Now, still with me? Only the half of the moon facing the sun will be illuminated. So, when Dr. Sarah looks at the moon, what's she going to see? Let me draw a line from her face to the moon.
That's the dark side.
Yeah, she's not going to see anything, right? It's just going to be completely black. This is what we call a new moon. This is what we call a new moon, where the bright or lighted part of the moon is facing away from the Earth. Now remember, the side of the moon that's facing the sun is always illuminated. The side of the moon facing the sun is always illuminated. But the question is, how much of the side that's illuminated is facing the Earth? And based on the moon's position relative to the Earth will depend on what part's illuminated. All right, guys, I'm going to move the moon a little bit. Is that okay?
Sure.
Yeah, we're going to move the moon. I'm going to put the moon here. But just like always, again, just like always, the half of the moon facing the sun is going to be illuminated. Awesome. Oops. Okay, so now as Dr. Sarah looks at the moon, there's more of the illuminated side facing her. Right? She can now see more of the illuminated side. As she looks at it, right, there should be y'all get the point, right? This is a very slender crescent that she's seeing at this point, right? Because the part of the moon that's lit is mostly facing the sun, but she's starting to be able to see a bit of it. This is a phase called the waxing. Waxing means increasing in size crescent. Jesse does not know how to spell crescent. Hold on, don't tell me. Right. No? Nope, that doesn't seem right. I think there's a C in it. Does anybody know how to spell crescent? Internet me out to go. Crescent. It seems like it should have a C.
That's AST.
Say again?
That's AST.
Okay, thank you, sir. I knew it felt like it should be like crescent. Waxing crescent, right? Again, the same part of the moon is illuminated, not same part, but the half of the moon facing the sun is illuminated. The only thing that's changing is the amount of that illuminated side that Dr. Sarah can see based on her position. So we started off with the new moon, and then we went to the waxing crescent. All right, now I'm going to move the moon some more. Let's keep going. You got to get all the way around. Again, the portion of the moon that's facing the sun is illuminated as always. All right. But now, as you can see, Dr. Sarah is able to see half of the illuminated side here and also half of the dark side. So for her, it's just going to look like what we usually call a half moon, but better called the first quarter. Any questions about the first quarter? Feel pretty good? All right. In that case, I'll speed up a little bit. We'll put the moon here. Again, the half of the moon facing the sun is illuminated, the other half isn't. Now, from Dr. Sayers' perspective, most of the moon is illuminated, but not all of it. There's still a dark sliver. Actually, the opposite of what she would see. The dark part would be on the left. Let's just fix it this way. Anyway, no wonder that's the left. This is what's called a waxing gibbous. It's almost a full circle, but not quite. This is a waxing gibbous. All right, I'm going to speed through these a little bit. I don't want to miss any of them. Okay, that's what I'm doing. At this point in the moon's orbit, the side of the moon that's facing the sun is the same side of the moon that's facing the Earth. Therefore, you can see all of the reflected side. This is what we call a full moon, even though what you're seeing is half the moon, right? You're only seeing half of it. But we call it full moon because you're seeing the fullness of the amount of moon that can be seen from the Earth's surface. Full. Imagine this is a whole circle. Full moon. What I want you all to notice is that these phases are being caused by the orbit of the moon around the Earth. The same amount of the moon is illuminated. It's just how much of that illuminated amount is facing the Earth from your perspective at a given time. All right. So here, I'm just going to draw the last 3 moons. Of course, like I said, same half of the, it's always the half of the moon facing the sun that's illuminated. from this position here, this one, that's what's called a waning gibbous. You'll notice that most of the moon is still full, but there's a little dark part over to the right. So waning gibbous. Moving around to this one up here. Again, you can see half of the illuminated side and half of the dark side. So at that point, we should up here. The light part should be on the left. Awesome. And this is what's called the third quarter. You may also hear it referred to as last quarter, third quarter, last quarter. They both refer to the same thing. And the last phase before it completes its orbit is here. And we're going to call this the waning crescent. Good job, Johnny. We've got the waning crescent. It's called a waning crescent because it's decreasing in size, and it's a crescent. Well, what you'll notice at this location, again, if she were able to see it, which she couldn't from this part, but if she were up higher, notice that she's in the nighttime area, and she's going to have a really hard time seeing that waning crescent because the moon's really close to the sun, and it's hard to see the sun at night. So if you're reporting a waning crescent to me, and it's been night for like 5 hours, I'm probably going to be like, right? Oh, it's going to be closer to the sun. It's not impossible, right? You can see a waning crescent at 7:30 at night when sun sets at 4 or something. But it just is going to depend. But notice that she would see mostly darkness and just a little bit of that light. Is this all making sense? Anything? Questions? Confusings?
No.
No, pretty straightforward. Awesome. And if you got questions you don't want to ask right now, feel free to just send me an email about it or something.
What about a blood moon?
Say again?
Blood moon?
I mean, which blood moon type are we talking about?
Like, I just, like, during Halloween or whatever, I think it was just before Halloween, had a big bright blood moon or whatever. It was a big red moon. I was wondering about that.
It happens.
Wow, no.
That's pretty much it. It could have been a lunar eclipse. There was a lunar eclipse around that time, which will make the moon super red. Also, I want to talk about eclipses. Goodness gracious, I waste a lot of time. First, I gotta write some stuff up here. Okay, these are all the main phases: the new moon, first quarter, full moon, third quarter. And the whole cycle takes about 28 days. It takes about 7 days to get from here to here. right? And not only that, it only spends about 2 days at those main phases, about here to here. It'll be in those main phases, but the most of the time it's in one of the other, what I call transitional phases. So this one, this one, this one, and this one are what I call the main phases, and then it transitions from that to this, right? And I guess I'll have to explain more about eclipses next time. But that's it for today. If you want to stick around and ask some questions, have at it. And I think I will answer your eclipse question after I turn this video off. I think we did a pretty good job today.